Assalamualaikum and hi everybody. Here I will show example solution process for chapter 4. Example 4.1 Weight. The question states the box with mass 2 kg rests on the top of smooth surface table. Determine its weight. From the question, the information we get is mass of the box equal to 2 kg. To determine the weight, we are using formula of weight. Weight equal to mass times gravitational acceleration. We substitute mass 2 kg and gravitational acceleration 9.81. Therefore, we will get weight of the box equal to 19.62 Newton. Example 4.2 Friction force. The coefficient of static friction is 0.800 between the soles of a sprinter's running shoes and the level track surface. Determine the static friction if her normal force is 60 Newton. From the question, we have information of coefficient of static friction equal to 0.800 and normal force equal to 60 Newton. To determine the static friction, we are using static frictional force equation Fs equal to coefficient of static friction times normal force. We substitute the information and the answer is 48 Newton. Example 4.3 Friction force. A block is moving with constant speed, experience 7 Newton kinetic frictional force. Find the coefficient of kinetic friction between the block and surface. Normal force exerted on the block is 25 Newton. According to the question, we had kinetic frictional force equal to 7 Newton. And also we have normal force equal to 25 Newton. And the question asks to determine the coefficient of kinetic friction. Therefore, we will use equation of kinetic frictional force Fk equal to mu Kn. And we substitute the information given. And we get the coefficient of kinetic friction equal to 0.28. For your information, coefficient of friction has no unit. Example 4.4 Forces acting on an object. A block on a rough horizontal surface is being pulled to the right. Draw all the forces acting on the block. Let's draw the figure. Since it's being pulled to the right, therefore it will move to the right. Therefore, the forces that acting on the block will be the pulling force, weight pointing downward, normal force perpendicular to the surface, and frictional force in the direction opposing direction of motion. We have frictional force since the block is moving on the rough surface. Example 4.5 Free body diagram. Draw a free body diagram for the figure below. In this figure, we can see that there is a picture frame attached to two different strings. Therefore, the forces that acting on the picture frame will be weight pointing downward, and we have tension. Let's label tension at the right as T1 and tension at the left as T2. For free body diagram, we will combine all forces in one point. It will be weak, tension 1, and tension 2. Example 4.6, free body diagram. The system shown in figure below is in equilibrium and the surfaces are rough. Draw 3 separate free body diagrams, show all forces that act on each block. Since the system is in equilibrium, therefore all blocks are not moving. First of all, let's identify all forces that acting on each block. We start with M1. M1 experience weight downward and also tension. M2 experience weight downward, normal force, tension with 2 different tension, and also frictional force to the right. Direction of static frictional force of M2 is pointing to the right because there is a tendency of the blocks to move to the left since M1 is the heaviest among all blocks. Lastly, M3. M3 experience weight downward, normal force perpendicular to the surface, tension on the string, and frictional force. We are using static frictional force since all blocks are in equilibrium. We will transform all forces acting on M1, M2, and M3 into 3 different free body diagrams. We start with M1. M1 experience weight and tension. You draw exactly the forces that you had determined from the figure without the body. For M2, since frictional force 2 and tension 2 is in the same direction, therefore we just overlap on the same line. And lastly, for M3, since the surface is inclined, therefore the free body diagram also inclined. As you realize, direction of weight always downward. Example 4.7, Newton's first law. A 0.5 kg frame is in equilibrium under the action of the forces shown. Find the magnitude of the tension in both left and right direction. For Newton's law problem, I advise you to draw free body diagram first. So, let's identify the forces acting on the frame. The frame experience weight downward. And then it also has tension on left and right string. Let's label T1 for the tension at the right and T2 for the tension on the string at the left. Then we draw free body diagram. The free body diagram will turn like this. Please take note that the frame is in equilibrium. Therefore, total force will be equal to 0. Since the mass of the frame is given, so why don't we calculate the weight first? We calculate weight by using formula weight equal to mass times gravitational acceleration, where mass is 0.5 and gravitational acceleration is 9.81. The weight is equal to 4.91 Newton. After we draw the free body diagram, second step is we construct a table with 3 columns. Containing column of X component and Y component. I suggest to you to using this table to resolve the forces. Since we have 3 forces, therefore we have 3 rows. This is for T1, T2, and weight. So we start resolving T1. T1 at X component will be T1 cos 30 and T1 at Y component will be T1 sin 30. Both T1 cos 30 and T1 sin 30 is positive because at X component it pointing to the right and Y component it pointing upward. For T2 at X component it will be negative T2 cos 45. It is negative because T2 cos 45 is pointing to the left. And Y component for T2 will be T2 sin 45. For weight, since weight is pointing downward, therefore, Y component for weight is negative. However, weight is not related to X component. Third step is we write the resultant of X component and Y component. Resultant of forces at X component will be T1 cos 30 minus T2 cos 45. And it is equal to 0. The resultant of force at Y component is T1 sin 30 plus T2 sin 45 minus weight also equal to 0. Both resultant of F at X and Y component is equal to 0 because the frame is in equilibrium. Let's label this as equation number 1 and this one is equation number 2. From equation number 1, we rearrange the equation. Let's make T1 as subject. And you will get T1 equal to 0.816 T2. From our finding, we substitute T1 equal to 0.816 T2 into equation number 2. We had calculated the weight before. Okay. Now we solve the problem and we will get 1.12 T2 equal to 4.91. Therefore, T2 is equal to 4.38 Newton. So, we had solved T2. T2 is tension on the string at the left. Now, we want to find the tension on the string at the right. So, we take T2 equal to 4.38 into this one. T1 is equal to 3.57 Newton. Example 4.8 Newton's second law. A 12 kilogram block which lies on a frictionless table is being pushed to the right with force equal to 5 Newton. Find the acceleration of the block. Since the block is being pushed to the right, therefore the block will accelerate to the right. Now, let's identify the forces that acting on the block, which is it has weight pointing downward and normal force. There is no frictional force because it states that the table is frictionless. The block is accelerating in horizontal. The only force that acts horizontally is pushing force, F. Therefore, resultant force at horizontal is pushing force, and resultant of force at horizontal will equal to MA. Therefore, F equal to MA. F is 5 Newton and mass is 12 kilogram. Here, acceleration of the block is equal to 0.417 meter per second per second. Example 4.9 Newton's second law. Two objects of masses m1 equal to 10 kg and m2 equal to 15 kg are connected by a light string, which passes over a smooth pulley. Calculate A, the acceleration of the object of mass 10 kg, and B, the tension on each string. Given gravitational acceleration G equal to 9.81 meter per second per second. First, let's identify the forces that acting on each object. We start with M1. M1 will have weight pointing downward. Let's label it as W1. And tension on the string. We label it as T. And for M2, also it has weight pointing downward and tension on the string. Let's calculate weight for M1 and M2. We calculate weight by using formula mg. Weight for mass 1 is 98.1 Newton. And weight for mass 2 equal to 147.2 Newton. We go to the next step by drawing free body diagram and construct the Newton's equation. We start with M1. For M1, we have weight 1 and tension. And M1 is accelerating upward. It's not necessary for you to construct X and Y component table since all forces in M1 and M2 are in parallel, which is it is at Y component. So we straight to the construction of Newton's equation, which is resultant of force for M1 is equal to T minus W1. And it also equal to M1A. So T minus W1 equal to M1A. Let's substitute the information that we have. Let's call it as equation number 1. Let's continue with M2. For M2, it accelerating downward. The resultant force for M2 is equal to W2 minus T. And it is equal to MA. So this one we call it as equation number 2. Question A is to determine the acceleration on 10 kilogram object. Means that acceleration on M1. Acceleration for M1 and M2 are the same since they attached together by using the same string. To determine the acceleration, we will do simultaneous equation. We will adding equation number 1 to equation number 2 to eliminate tension. Therefore, we will get here the acceleration is equal to 1.96 meter per second. Next question is to determine the tension on the string. Since we have acceleration equal to 1.96 meter per second, we can substitute either in equation 1 or equation 2. I want to substitute into equation number 1. And tension on the string equal to 117.7 Newton. Example 4.10 Newton's second law. A 5 kg block A which hangs from a string which passes over a frictionless pulley and is joined at its other end to a 2 kg block B which lies on a rough table with 5 Newton kinetic frictional force. Find the A. Acceleration of the two blocks, B. Tension in the string, C. Coefficient of kinetic friction. Since block A and block B are attached together, block A is pulling block B. Thus, block A will accelerating downward while block B accelerating to the left. Let's start with identifying the forces that acting on object A and object B. For object A, it has weight pointing downward and tension. And for object B, also it has weight pointing downward, normal force, perpendicular to the surface, tension, and frictional force. Direction of kinetic frictional force always oppose direction of motion. Now we draw free body diagram and construct resultant force for block A and block B. We go with block A first. For block A, we have tension and weight, and it accelerating downward. The resultant force for block A should be WA minus tension. And the resultant force is equal to MA. Let's substitute the information that we have. Let's call it as equation number 1. For block B, we have weight, normal force, kinetic frictional force, and tension. For block B, we need to consider resultant force at X component and Y component. Let's do for X component first. Resultant force of block B at X component is equal to T minus kinetic frictional force. And it is equal to MA. Given kinetic frictional force is 5 Newton and mass for block B is 2 kg. This one we write it as equation number 2. The resultant force of block B at Y component is equal to N minus WB. And the resultant force of B at Y component is equal to 0 since there is no motion at vertical. This is, we call it as equation number 3. First question is to determine the acceleration of two blocks. So, we will do simultaneous equation by adding equation number 1 and equation number 2. And we need to eliminate tension. Here we get acceleration of two blocks equal to 6.30 meter per second. Question B is to determine the tension on the string. So I will substitute acceleration into either equation 1 or equation 2. This time I choose equation number 2. And the tension equal to 17.6 Newton. The last question is to determine the coefficient of kinetic friction. We can use formula kinetic friction equal to coefficient of kinetic friction. In the question, the kinetic frictional force is given as 5 Newton. However, we need to determine normal force first. To determine normal force, we will use equation number 3. Let's look at equation number 3. Equation number 3 state that N minus weight of block B equal to 0. So, we will get N normal force. Therefore, the coefficient of kinetic friction is equal to 0.255. Example 4.11, Newton's second law. A block with mass 7.5 kg is released from an inclined plane with an angle 30 degrees as shown in figure below. Assume that the block slides downward and experience a sliding friction force with coefficient of kinetic friction mu k equal to 0.25. A. Draw the force acting on the system, and B. Calculate the weight of the block and kinetic friction. Since the block slides downward, therefore the block accelerates at this direction. For question A, we want to draw the force acting on the system. Therefore, we need to draw again the figure. The forces that acting on the block is weight. We draw from the center of the object, pointing downward, and we label it as W. It has normal force. We label it with symbol N, perpendicular to the surface, and kinetic frictional force in the direction opposing the direction of acceleration. For question B, we need to calculate weight of the block and kinetic frictional force of the block. To calculate weight, we are using formula of weight, W equal to mass times gravitational of acceleration. Mass of the block given as 7.5 kg and gravitational acceleration is 9.81 meter per second. Therefore, weight of the block is 73.6 Newton. To determine kinetic frictional force, we are using the formula of Fk equal to coefficient of kinetic friction times normal force. Here we lack of normal force. We need to find the normal force first. To get a clear view, let's draw the free body diagram. We have weight here, normal force, and kinetic frictional force. The plane is inclined at angle 30 degree. From the free body diagram, we can see that normal force is in vertical line parallel to W cos 30 and it is in equilibrium. Therefore, we find the resultant force at vertical. It is equal to N minus W cos 30 and it is equal to 0. From this, we will get N is equal to W cos 30, where W weight is 73.6. Therefore, we get normal force as 63.7 Newton. Then we can substitute into formula of kinetic frictional force, where the coefficient of kinetic friction is 0.25 times normal force 63.7, and we get the kinetic frictional force 15.9 Newton. Example 4.12, Newton's second law. A horizontal force is exerted on a block for it to slide up an inclined plane as shown in figure above. Assume that the block slides upward and experiences a sliding friction force with coefficient of kinetic friction mu k equal to 0.01. Let the weight of the block is 15 Newton, force equal to 20 Newton, and angle theta equal to 20 degree. A. Draw the free body diagram, and B. Calculate the acceleration of the block. In the question, it gives you weight of the block. So, let's start determine the mass of the block by using formula W equal to mg. Here we will get mass of the block equal to 1.53 kilogram. For question A, we want to draw free body diagram, so let's identify the forces that acting on the block. We have weight pointing downward, and we have normal force perpendicular to the surface. Since you push the block sliding upward, therefore it will experience upward, and it will has kinetic frictional force opposing to the direction of acceleration. Now, let's transform these forces into free body diagram. For free body diagram, we will combining all forces in one point. We have weight, we have horizontal force, and then frictional force, and normal force. Don't forget to put direction of acceleration. We want to determine the acceleration of the block. I suggest to you to draw again the free body diagram, including the inclined angle. The surface is inclined at angle theta 20 degree. So here we will assume this will be x axis and this one will be y axis. Don't forget to include direction of acceleration as guiding for us to determine the sign convention. Okay, so as you can see, we need to resolve the forces into x and y component. So let's start with the table with 3 columns. First column is for forces. This is x component column, y component column, and here we have 4 forces, therefore we have 4 rows. For normal force, it is at y component. For kinetic frictional force, it is at x component, and the direction is opposing direction of acceleration, so we need to put the negative sign here. However, it's not related to y component. The force F, the pushing force, so we need to resolve into x and y component. For x component, it will be F cos 20, and it is positive because it has same direction with acceleration. However, for y component, it is negative, F sin 20. since it pointing downward. And for y at x component, it will be negative w sine 20 since it pointing to the left, opposite direction of motion. And for y component also it is negative w cos 20. For resultant force for x component will be negative Fk plus F cos 20 minus W sin 20 equal to MA. Let's substitute the information that we have. Therefore, we will get 13.7 minus Fk equal to 1.53A. And this is as equation number 1. Now we will do for resultant force at y component. N minus F sin 20 minus W cos 20, and it is equal to 0. When we substitute the information, it will be N minus 20.9 equal to 0. Therefore, from this, we get N equal to 20.9 Newton. We will substitute into equation number 1 to obtain A. Let's find the kinetic frictional force. Fk equal to mu Kn, where mu K is equal to 0.01. Therefore, the kinetic frictional force equal to 0.209 Newton. Then, by using equation number 1, we get the acceleration equal to 8.82 meter per second per second. Example 4.13, Newton's third law. A box of mass 15 kg rests on a smooth horizontal floor next to a box of mass 8 kg. If you push on the 15 kg box with a horizontal force of magnitude 36 Newton, A. Calculate the acceleration of the boxes, and B. Calculate the contact force between the boxes. Now, let's identify all the forces that acting on box A and box B. For box A, it has weight pointing downward, normal force perpendicular to the surface, pushing force F2, and since box A is in contact with box B, therefore it has contact force. Let's call it as FAB. For box B, it has weight, normal force, and also it has contact force perpendicular to the surface of box A. Let's call it as FBA. Here, FAB and FBA is action and reaction force. They have same in magnitude, but opposite in direction. Next, we will transform all of these forces into free body diagram. Let's start with box A. For box A, it has normal force and weight. The pushing force F2 and contact force FAB. Don't forget to include the direction of acceleration. We have resultant of force for box A at X component, which is equal to F2 minus FAB. The resultant force of box A at X component also equal to MAA. Then we can simplify F2 minus FAB equal to MAA. Let's substitute all the information that we have. Pushing force is given as 36 Newton. Mass of box A is 15 kilogram. Let's call it as equation number 1. For box B, it has contact force, normal and weight. The resultant force of box B at X component is equal to FBA. And the resultant force of box B at X component also equal to MA. Therefore, FBA equal to MBA. Here, mass of box B is 8 kg. So this is number 2. Since FAB and FBA is a contact force, they have same in magnitude but opposite in direction. Then we can substitute FBA into FAB in equation number 1. And here, the acceleration is equal to 1.57 meter per second. Question B, we want to determine the contact force. So I will use equation number 2. FBA is equal to 8A. We substitute the acceleration that we had get from question A. And we get the contact force as 12.6 Newton.